yes. I kept thinking, well, yes, but it's also
Okay, so table salt. Everybody has experience with solid table salt, yes? If not, you've been living a bland life, right? It literally gives us flavor. So what happens, right, when we dissolve it in water? Okay, it becomes electrolytic, right? The solution itself. And the way that we note it is there's two different ways we can do it, okay? There's this NaCl with an AQ behind it. Right, it means aqueous. Some people pronounce it aqueous. It doesn't matter. It's the same thing. The emphasis is on a different syllable, right? It's the same words, okay? Yeah, syllable. 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 Syllable, right? Wherever you're putting the emphasis. Okay? So if you see an AQ as the state behind it, there's generally 4 states of matter we see. Solid, liquid, Rohan, Louis. Those are the 4 states we see.
You forgot plasma.
Right? Okay, so solid, liquid, gas, aqueous. Right? Behind, we're going to get to, after President's Day weekend, we are going to get ourselves to chemical reactions and writing them. And I think you have some experience with it. We know that we have states of matter. Okay? Aqueous means that this substance is dissolved in water. Now, with ionic compounds, okay, with things like NaCl, how do I know that's ionic? Right, one's from left, one's from the right, metal, non-metal, okay, we're looking at that. We could look at the electronegativity difference, and it would be above 2, okay, all that. What really happens in the solution, right, is the Na and the Cl dissociate from each other, okay? The water pulls them apart. So there's actually like a third spot or a third way that we can write this where we say that there is Na ions and Cl ions. Okay, and they're ions because they're charged. Okay. In the middle, when we say NaCl aqueous, it's giving the impression that the sodium and chlorine hang out together while they're in the water. That is not true. Okay. So when people write ionic compounds as aqueous, it's understood from our learnings in chemistry that what's really happening is on the far right. The sodium ions and the chloride ions are no longer associated with each other. The word we use is they dissociate. Okay? Basically what's happening is the ion dipole forces of water to the ions is stronger than the ion-ion attraction between sodium and chlorine. Okay? So the water has enough energy to pull apart the electrostatic force of sodium chlorine because the ion dipole force, the intermolecular force between those two, is stronger. It's all about being energetically favorable, right? Back to that as well. So this is what's happening with ionic compounds. Put another ionic compound and you will see the same thing, okay? Where the ions are dissociating from each other. Now, if you bring in something like sucrose, okay? Sucrose is table sugar. Okay, things you put in your what do you call it? Coffee, tea, right? That stuff to sweeten. Beverage, there we go. That's glucose.
You go, Rohan. Sorry.
Wait, hold on. C12, H22. No, H20. What is it?
It makes 24, right? Because like CH2 is O is the format.
Is it O11?
12. It has to be 12.
It's 11. No, because the oxygen is bonded. Oh, no, that's glucose. We want sucrose. Because of the bond in between, the oxygen is not bound to a hydrogen.
Okay. Wait, what did we say?
C12, H24, O11.
C12, H22.
H22! We did have that. It is 22.
I got it wrong and I Googled it.
Okay, here's a little bit more. Here's a little bit more information. Does anybody know like the general class of sucrose? Like what do we call those molecules? Carbohydrates. Okay? What do you hear in carbohydrate?
Carbon.
Carbon.
Oh, didn't we do
I hear carbon. Does everybody hear carbon? And when you think about hydrate, does anybody think about just straight up hydrogen? When somebody goes tell you, go hydrate. You take hydrogen?
Oh my god.
Water.
Whoa, go.
H22O11, if you bring that down to its empirical formula on that side, H2O. There's just 11 of them in the molecule of a carbohydrate. It's kind of cool, right? Fun science, it's helping you. Rohan?
Is there like a normal you're doing like labs and stuff with like these chemicals?
Yes, but we wouldn't have done any just quite yet. When we get into chemical reactions, we're going to see what we can do. We're definitely going to do precipitation reactions because that's stuff you can do right at your desk. But we can't blow things up in here because there's no hood. What? Yeah, we might actually do it in the spring because we can go outside. We can blow something up outside. Okay, but sucrose, we know is a solid. Does sugar dissolve in water?
Yes.
Yes, we know that, okay? If you look at the sugar in your sugary drinks, there is a almost incomprehensible amount of sugar that is dissolved in those drinks, and that's why they are so addictive, and that's why you keep drinking the sugary drinks, okay? If you drink coffee and you put a lot of sugar in it, do you actually like coffee? No, no, you like sugar, and then something about the caffeine, but you probably are getting more of a sugar high than a caffeine high.
Why do we all like water with sugar? Why don't we just put water directly into sugar?
Some people do. Has anybody seen Men in Black? Anybody? Bueller?
Yeah, sure. With Will Smith?
Tim? Have you seen it?
I mean, I don't know. There's like a vague like zone of memory in my.
Yeah, the alien drinks sugar water. He wanted sugar water, right? So here's the thing. Sugar has a really high. You can dissolve a lot of sugar in water compared to other substances. So like, if you have 100 grams of water, you can dissolve like 20-something grams of salt, right? So like seawater. For sugar, you can actually dissolve more sugar than there is water at certain temperatures. So if you have 100 grams of water, you can dissolve more than 100 grams of sugar in it at certain temperatures. It's insane, okay? It has a really, really high solubility, and that's what people are exploiting when they're selling you sugary drinks, right? So it all comes together in all of this, right? So anybody, I think it is Gatorade. They say they have carbs to fuel you and electrolytes to replenish you. So what do they have in their drink? Sugar and salt. They're literally telling you scientific words for sugar and salt. Okay?
Really?
But they're telling you carbs are fueling you, right?
So sad.
And they're telling you that the electrolytes are replenishing you, which is true. But most of the time if you're just drinking Gatorade on like a normal day when you're not sweating too much, or even if you're just like out for like, you know, a leisure jog where you're not sweating a lot, you're putting in more than you actually need in terms of fueling and also replenishing. So just think about it, right? They're being scientific-y to sell you on salt and sugar in a good proportion, and it tastes really good with all the other stuff that goes with it, but
It does say that.
There's a lot of
It does say
yeah.
I thought that
Carbs help you breathe.
doesn't salt like dehydrate you though?
By itself, yes, if there's like nothing else. So yes, if you are,
Yeah. I was like, so basically they're giving you a drink.
That's true. It does.
so there's like,
That
so
kind
if
of
you're not sweating and you drink salty water, like straight up like seawater, that is bad news.
Yeah.
But you know that when you sweat, you like taste salt, right? So you need to replenish some of your electrolytes in there. But if you're, so if you like drank 100 million gallons of Gatorade in a short period of time.
Is that even possible?
No, but if you did, then you could potentially die from dehydrating yourself, even though you're hydrating yourself.
Oh, so the inverse.
The dose makes the poison.
Why does
Okay.
ice cream make you thirsty?
If you drink too much water, you could, in theory, die, but you need a lot of water to do that, right? You would actually hypertension, you know, with the cells and the exploding and crippling. Yeah, so it'd be bad. It would be bad. Okay, so, I love digressing because it's so, like, you can see what's happening. But here, when C12H22O11 solid dissolves in water, can it dissociate into ions?
Possibly. Oh, no.
It is what type of compound?
Miscible.
Missable.
Nope. What type of compound? Covalent compound. It's all nonmetals hanging out together, right? They're covalently bonded. They do not dissociate from each other. So what we would show,
So it's just chilling.
it's just chilling. It is dissolved, right? It did dissolve in water. So it just stays as aqueous. There's nothing else that it does, is it just gets down to that smallest piece of C12H22O11, all bonded covalently, and that's it, right? It doesn't do anything else. So the electrolyte has ions present, and it's the free flow of ions that allow for the conductivity of electricity, okay? Sugar water, if it's in distilled water, tap water has ions in it, so that's why tap water does conduct electricity. But if it's distilled water with no ions present, just H2O, and you dissolve sugar in it, dissolve sugar, it wouldn't conduct electricity because there are no charges able to flow. Rohan?
About like solubility and miscibility.
Yep.
If you have two liquids that dissolve, will they always be miscible?
I believe so,
And if
yes.
you have like two different forms that dissolve, will they always be soluble?
Probably, yes. From my experience, similar phases, mostly liquids, gases do it too. Liquids and gases, similar phases, if they are soluble with each other, they will be miscible. They will continually mix with each other, no problem. But when you take a solid, mix it in a liquid, then you have a point in which it stops dissolving. Sugar does have a high solubility, but it is not completely miscible with water. There will be a point where your sugar doesn't dissolve anymore, even at high temperatures, okay?
Like, you know, like small thing of water, like a full bag of sugar, it's not gonna dissolve.
It could, so it depends on, like, it's more than just temperature, but like, you can get times where you can dissolve double the amount of sugar in the volume of water you have, right? So I'm not saying a bag of sugar will dissolve in 1 gram of water. I'm not saying that, but like, you could dissolve. There is a temperature where you could dissolve 2 or 3 grams of sugar in just 1 gram of water. It's crazy. It looks weird. It gets discolored a little bit. It becomes viscous, right? No longer looks watery. It looks kind of like globally. I don't know how to describe it. Okay.
Sugar in a Coke can doesn't fit in the can. What?
What?
It's like 60 grams of sugar, and that can does not fit.
Oh, I heard a different word. Oh, okay.
Cocaine.
Yeah, that's what I heard. Oh, yeah. Anyway,
A can of Coke, that's like massive.
I mean, that used to be an ingredient in
I
Coca-Cola.
was like, oh.
Okay.
I was like, oh, I didn't know.
Okay, so are there any questions about this, or are there questions about what you listened to, watched, took note of in the video from yesterday? Feeling decently comfortable, kind of making sense. Have we dealt with concentrations before, or with solutions before in 8th grade chemistry, whenever you did it? Kind of, maybe.
Yeah, I know we did.
But like this idea of mixing and dissolving and stuff like that. Okay, so where we're going today is we are going to try, now here's the key word, okay? We are going to try, we're going to give this an effort in that we're going to watch a video tonight that is explaining using concentrations, okay? But what I wanted you to do in class today is I'm going to give you a little primer, but then there's going to be some questions that you're going to ask. And you're going, I don't know how to do this. And the answer is, yeah, I know you don't. Let's just try. Let's see what we can do with the knowledge that we have without direct instruction on what to do and see where we get, okay? So looking at this is a chart of different concentration units, okay? Just like mass has different units, grams, kilograms, ounces, pounds, right? There's different units we have for different measurements. Concentration is the same thing, okay? And there's a definition. Most of our concentrations are calculations, okay? What are we using to calculate? And it helps us quantify, right? Because you can look at something and say, look, that is dilute compared to this is very concentrated, right? Strong concentration, dilute concentration. But that's all relative to each other, okay? Here, we are putting numbers to it, and we're getting actual values, okay, so that we can quantify how much do we have in our solution. So there's a few different ones. The most important one that we are going to utilize this year is molarity, okay, and that is because we're dealing with moles, right? Moles is a chemical unit for us, and also one of the easiest things to measure is the volume of the solution, okay? because all you need is a graduated cylinder. If the stuff is already dissolved in the solution, I just need to measure out the volume, and that's that. Okay, so molarity is the most common chemistry unit of concentration. How you find it is you take the moles of your solute and you divide it by the liters of your solution. Okay, and it's that simple. You take that quotient and there's your answer, right? So if I had 1 mole dissolved in 1 liter, right, I would say I have a concentration of 1 molar solution, okay? Or my molarity is 1. The unit is capital M, or moles per liter. Then molality, I know they sound a lot alike, right? The literal only difference is an L and an R in the middle of the word, but they mean different things. They both deal with moles, right? But on the bottom, on the denominator of molality, is mass of the solvent in kilograms, okay? So what we're dealing with in our concentrations is just what are we using to calculate this concentration? So if I can find my moles and my liters of my solvent in solution, I can calculate the molarity. If I know the moles of the solute and the mass of the solvent, I can calculate the molality, right? So it's just using these definitions and figuring out how can I get the information I need from what I have to calculate the concentration I am interested in. Rohan? Yeah, so that M is weird. It's not, because lowercase m regular stands for mass. So this is more like I do it like a script M or an M with a tail. Like I think they do it as an italicized M, but the font they chose doesn't show that very well. That is for the unit, right? So variable, lowercase m is mass. Lowercase m unit is meters. So we have to do something different. They do an italicized M for molality. And then we have mole fraction, right? Anytime you take a fraction, it's part over whole, right? And what's the difference between mole fraction and mole percent? Right, one is just times 100, right? So they're similar to each other. We just, if I want to be talking about the percentage, right? Or if I want to be talking about the fraction. And then we have parts by mass. We have done this before, right? The mass percentage is the percent by mass out of 100. The thing that we're adding is this idea of parts per million and parts per billion. They sound scary, but actually percent by mass can also be known as pph. What does that H stand for? Parts per 100, right? All we're doing is taking the ratio of the mass of the solute over the mass of the solution and multiplying it by some factor. We are so used to calculating by multiplying by 100, right, to turn it into a percent. Mass, ppm and ppb are the same thing. We are just multiplying them by either a million or a billion. And the reason for that is some of the things that we track in waters or in solutions have a really small concentration, and they can be very harmful in really small concentrations. So instead of talking about a 0.0001% solution, I can talk about a 0.1 or even something, or 0.1 ppm, or even a 100 ppb, right? Numbers that we like to work with are closer to 1, right? So we don't want to deal with a number too large. We don't want to deal with a number too small. So what we do is we figure out a way to calculate it to get it to a working number. Okay, but notice parts by mass, if I'm doing percent ppm or ppb, I'm taking mass of solute over mass of solution and then multiplying it by whatever factor I'm interested in. They're all related to each other. Okay?
Percent by
Yeah.
mass, I'm a little confused. Is that the same thing as parts per million? I'm a little confused what that is.
So it's all of those are related in that, like, when you're, so think about mole fraction versus mole percent, right? They're similar. We're just multiplying by 100 to get to the percentage. Same thing's happening here with percentage, parts per million, and parts per billion. I'm taking the ratio of the masses, and then I'm multiplying it by some factor, either 100, a million, or a billion, depending on what I'm looking for. And again, the reason why we do that is to get numbers that are more workable, right? I don't want to work with 0.000005%. I want to work with a number that is like maybe 5 parts per million or 500 parts per billion. Easier numbers to work with. Or I would say comprehend, right? Because a really small percentage, you're like, what? Like, that's really, I can't wrap my head around it. So instead of a really small percentage, I can say, oh, if it's 10 parts per million, that means for every 1 million grams of my solution, I have 10 grams of my solute. Oh, okay, right? You can make sense of those numbers. Okay, so what we're going to do is I'm going to set you free to try to work on some problems in mastering chemistry, okay? I understand we do not have direct practice together via video or in person on these problems, but I want you to work on your problem solving skills. Okay? I want you to work on, I know that I need to get to moles of this and volume of that. How do I get there from what I have? Okay? So on mastering chemistry, there should be a 4.6, I think it is, solution concentration in class problem set. Okay, so go ahead and pop into that. I mean, do you have your headphones with you today?
Yeah.
Would you be able to pop into Zoom for me so that you can work with Kaylee?
Right next to it for like.
420.
4.6. It should say solution concentration. Whatever number it is. Is it there?
Yeah.
What? Oh wow, it's hard. And still, if you're